So hello guys, my name is Mohammad Izhaan Khan. Currently I'm pursuing my bachelor's degree in civil and environmental engineering from IIT Patna. Okay, so in the last session we were doing the exemplar questions of the topic dual nature and radiation of matter. Okay, so let's check. We had done the question number 13th in the last class. Okay, so it was the last question. Now moving onwards, today I'll start from the question number 14th. So basically, I told you the gist of this topic that you need to understand the interconversions of the formulas in it, because basically what happens is the questions which can be made out of this topic are basically for the relations. They are basically you just have to relate. They'll give you two three values like they'll give you the mass for the alpha particles. You already know mass for alpha, mass for proton, mass for electron, and they ask you to compare the reproduktive wavelength or anything else for that matter. So it's a simple topic. You just need to be well conceptual in this. Okay. So moving onwards to question number 14th, and wherever I see that you need any help and I need to tell you something important, I'll just indicate it. I'll show it all to you. So it is a revision kind of class, so you don't have to worry about it. Only. So moving onwards to question number 14th. So a proton and an alpha particle are accelerated using the same potential difference. Call it how are the d probably wavelengths lambda p and lambda a related to each other. See, I told you basically like this is the generic kind of question. So what happens is, do you know the formula for lambda? H upon momentum. Okay, this is for d probably wavelength. Now I'd ask you one thing. For the kinetic energy, you can write like this. Or like if I multiply mass on both the sides, it will be like this. So 2 me will be equal to what? P square mv whole square. So momentum can be written as under root of 2 me. Simple. So this can be further written as underscore 2 under root, I'm sorry, under root 2 me. Okay. And what about energy? So by electrostatic, the concept ये होता है कि basically what is potential difference? अगर इतने में potential difference भी है, so this is the energy that is developed when a charge of Q passes through it. Okay, so energy which is developed is Q times V. Alright. So now in the place of E, I can write QV. Lambda is equals to H upon 4 under root of 2NQV. Alright. So this is the formula for lambda which we have developed till now. Now we have to check what has been given to us in the question. So there's a proton, there's an alpha particle. Okay, same potential difference. That means B is same. Okay, so the proton has a different charge and an alpha particle has different and M is different. So we have to compare lambda is inversely proportional to under root MQ. The rest all the things are same. Alright. So now, so I write for lambda P upon lambda for alpha particle. Alpha will be equal to whole under root of mass alpha curve and charge alpha curve divided by mass proton curve and charge of proton. So now putting in the values, mass alpha is 4 times mass of proton and charge of alpha is 2e whole divided by mass of proton. Charge on proton is E. It will be under root 8. So lambda P upon lambda alpha is 2 under root 2. Okay. Now what? Yeah, lambda P equal to lambda alpha. We have developed this relation. Under root 8 times lambda alpha. This is the relation. Okay. So moving onwards. The next question we have is question number 15. So now, okay. So I'm sorry. I have done this question in the last class. Okay, question number 14, question number 15 I've done. Okay. So we have to start from question number 16 now. So it is good. It was a good question, and it is good for your revision, and it might work as a warm up for you. So now question number 16, please. Now, in question number 16, there are materials which absorb photons of shorter wavelength and emit photons of longer wavelength. Okay. Can there be a stable substance which absorbs photons of larger wavelength and emit light of shorter wavelength? So in the first case, the materials which absorb photons of shorter and emit photons of longer wavelength. When the material which absorbs the photons of shorter wavelength, it has the same energy of incident photon on the material. Okay, and the energy of emitted photon is low when it has longer wavelength. That we already know. So basically, we can say this, like, see this. This is the material. Let's say material is I. So shorter wavelength photons. P of shorter wavelength is incident on it. Okay, so it is high energy. It is high in energy. It has been emitted. So the energy that it is getting, like E in, is high, but it is emitting photons which have higher wavelength, higher wavelength range. So the energy which is giving out is less. So E in is more, E out is less. Okay, this is the first case. Like in the first case, case one, I can write like this: E out is greater than E in. Okay. In the second case, the energy of the incident photon is low for the substance, which has to absorb photons of larger wavelength. Okay, because the wavelength is large, the energy will be low, and energy of emitted photon is high to emit light of shorter wavelength. Okay, this means that material has to supply the energy for the emission of photons. Okay, let me just put it simply to you. And emit light of shorter wavelength. Again, the same thing. If they absorb photons, photon of shorter wavelength is high in energy, and photon of large lambda is low in energy. So there is an imbalance of energy when it is gaining the photons of shorter wavelength and emitting photons of larger wavelength. In this case, what is happening is whenever E out is greater than E in, this means that material has to provide some energy. So this is not stable. So not possible for stable compounds. Okay. Now let's see the next question. Question number 17. So basically, there is a short answer kind of question. Maybe. So all the electrons that absorb a photon come out as photoelectrons. Okay. So there is a very nice explanation for this. Suppose that this is a disk. I'll try to draw as good as I can. So just bear with me. And you have to suppose that it has been filled with electron, 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 and electron. Okay. So basically, what do you know till now? You know that kinetic energy max, K max, is equals to the energy provided by the incident photon minus the work function. But why is it written K max? Think of it like this. Suppose you provided some energy E onto this, and the work function. Work function means how much energy is required to pop this electron out of this disk is 5. So the kinetic energy by the conservation of law should be E minus 5. But why is it written K max? You need to understand this to answer this question. K max means what happens is you provided this energy E. 5 was the work function which was definitely taken out of this E. So now you are left with E minus 5 energy right now. The electron right now which is getting out of here is having E minus 5 energy. But since electron repulsions are there, and it needs to move through these set of electrons, this sea of electrons, it needs to get out, and it is facing repulsive forces out of these electrons. So some energy will be lost in moving through these electrons. So there are many chances that this electron will, whatever energy it has, let's say it has E minus 5 energy initially, will drain out all its energy in just moving through this sea of electrons. So it may be left with a kinetic energy equal to zero. It may be left with a kinetic energy equal to E minus 5 by 2. And sometimes it may happen that whatever was the maximum kinetic energy, it did not attack any other electron. It simply got out. It was, let's say, at this point, it simply got out of there. So it can have the K max of E minus 5. So this is an important concept, and this will answer the question that was which question was it? Question number 17. All the electrons absorb a photon come out as photoelectrons. No, this does not happen. So this was just a basic way of telling you. Now let me give you the correct answer which you can write for this. So the key concept you know. Okay. So in the photoelectric, let me draw that cathode and the not diode. Okay. So this is a disk out of which we are taking the electrons, and some energy E has been provided to it. Okay, these are light radiations. Light radiations. All right. The electrons move out of this disk and start to move in a straight line, and they reach disk Q. Okay, where this is the anode and P is the cathode. All right. Now there is an experiment that is conducted. Okay, they connect a battery through it, and they vary the potential difference against this battery, and they also connect an ammeter over here to check for the current that has been passing through. Okay, it is a very complex circuit. I'm just showing you something. So what happens is they increase the potential difference to see that how many electrons are coming out. Okay, because the flow of electrons develops current, and they just vary the potential difference till the current through this ammeter reaches the value of zero. And for this potential difference, they calculate that how many electrons must be coming out. And by the light radiation, by the energy method, you know the formula already. You can calculate how many electrons should be coming out theoretically. So they find out that the theoretical number is way less than is way more than the actual electrons that are coming out. This means that most of the electrons which absorb this light radiation are maybe scattered inside the disk only, or maybe they just if they plug out of here, then the potential difference that has been developed will make it move. But most of the electrons will have the potential, will get the energy that has been provided by the light, but they'll dissipate this energy in colliding with the other electrons. So that is what I was trying to make you understand in the previous thing that I drew. So that is the basic concept for this. Now, question number 18. So there are two sources of light, each emitting with a power of 100 watt. One emits X-rays of wavelength 1 nanometer and the other visible light at 500 nanometers. So find the ratio of number of photons of X-rays to the photons of visible light of the given wavelength. All right. So the concept required here is X-rays. Right over here. E concept for X-rays. I'll write down some concepts for you regarding X-rays I have with me, and that will help you answer. Now, write the concept number 1. All right. There was a scientist named Roentgen. Roentgen was the man who found out about, who discovered about these X-rays. So Roentgen discovered that when a pressure inside the discharge tube is kept, how much? 1 yeah, ml of mercury and potential difference of same 25 kilowatt potential difference of 25 kilovolts. Then X rays are developed. So this is the concept number one. You have to note down these values, alright? Important. And in the discharge tube. Okay, so this is the concept one. Another thing you have to write. Now there are some requirements for production of X-rays. Requirements for producing X-rays. So number one is source of electron must be there. There must be an arrangement for the acceleration of these electrons. Arrangement for acceleration of electrons. Number third will be a target of suitable material. Like the material should be highly dense. Mass should be more. Let's say what is the number I can't recall right now, but this is it. This should be a target of high atomic weight. Let's just take this because higher atomic weight means higher melting point, so that helps us. High atomic weight. You have to check for this number. Okay, check for this. So note down this. This is the basic concept behind the X-rays. So because X-rays you can't usually like like most of the people don't pay heed to X-rays, and I'll say that it is not very important for the examination as well. But sometimes it means one question may come out of this. So whatever I wrote right now, that is enough for X-rays. Test we can solve by simply doing the wavelength and other formulas. Okay. So what has been given to us? Power has been given a 100 watt. Lambda 1 is 1 nanometer and lambda 2 is 500 nanometer. Okay, so I'll write N1 slash N2 as the number of photon of X-rays and visible light. Got this? So N1 is the number of photons, N2 is the number of photons for visible light. Alright, so T by D equal to P equal to NHC by lambda NHC upon lambda 1 equal to N2 E by T power N2 HC upon lambda 2. That means N1 upon lambda 1 equal to N2 upon lambda 2. Okay. So now putting on the values for it. Okay, N1 upon lambda 1 equal to N2 upon lambda 2. That lambda that is being given is 1 nanometer and 500 nanometer. So it will be 1 upon 500. Okay, so this is the ratio of the photons that have been emitted. This for X-ray, N1 is for X-ray, and lambda 1, sorry, wait. It will be N1 upon N2 equal to lambda 1 upon lambda 2. So that is 1 upon 500, and N2 is the photons for visible light. So let's take the next question, which is question number 19. So consider a metal. How did you consider the momentum conservation? Consider figure is not given to us. Okay. How would you reconcile the momentum conservation? Note light photons have momentum, different directions of the electrons. Okay. So what is happening is there is a metal. Okay. How would you reconcile with momentum conservation? Light photons have momentum in different directions than the emitted electrons. Okay. This is the way light is coming over it. And this is the way the electron is moving out of this. Alright. So the momentum of incident photon is transferred to the metal during this photoelectric emission. That like there are photons in this, and the momentum P of photon has been transferred to this metallic sheet. Alright. So at microscopic level, atoms of the metal absorb these photons, and its momentum is transferred to the nucleus and electrons. Like, see, at the atomic level, if you will go on this metal, you will see that the momentum that the photon carries has been accepted, has been absorbed by the nucleus and also by the electrons that are covering the nucleus. So the excited electron then is emitted out. Like this is the nucleus and this is where an electron is. Okay. So there is some binding energy, but the momentum of the photon is coming and has been absorbed by this nucleus and some by this electron. So due to this momentum, this electron pops out of this network, and this is the electron which may get the enough energy to go out as photoelectron. Therefore, the conservation of momentum is conserved in this case, as the momentum of incident photon has been transferred to the nucleus and also to the electron which is moving on. So the momentum conservation theorem is acceptable. It is valid for this as well. So moving onwards, we have question number 20th. Now we have to consider a metal exposed to light of wavelength 600 nanometers solid. The maximum energy of electron doubles when light of wavelength 400 nanometers is used. Find the work function in electron volt. Okay. So work function is what? Threshold energy. Okay. So that is the minimum energy of incident radiation that is required to eject the electron from the metallic sheet. That we already know. Like this. The formula K max. There is a formula by Einstein. Okay. So E minus work function. This is the minimum energy. Minimum E required to eject the electrons out of the metallic surface. Okay. So work function will be HV naught. It can be written as HC upon lambda naught, where this V naught, this is called the threshold frequency. Threshold frequency. Like this is the minimum frequency. Okay. This is the minimum frequency of light which can be used to eject the electrons, and this is the maximum lambda which can be used. This is called threshold wavelength. Okay. So now putting on those formulas, it was 12,000. Okay. So work function can be written as 12,000 on lambda naught in angstrom. Okay. K dash max is 2 times K max. It has been given to us. Okay. According to the problem, the first condition was when lambda was equal to 600 nanometer. For the second condition, the wavelength was 400 nanometers. Okay. So 600 nanometer and 400 nanometer are the two conditions that have been given to us, and also the maximum kinetic energy for the second condition. This is for the second condition. Okay. This is for the first condition. It has been given to us. Now, T dash max can be written as HC upon lambda minus 5 work function, and let me write it on expression. And 2K max, if I write over here, will be equal to HC upon lambda dash minus 5 naught. Okay. So if I write it 2 times 1230, let's see, HC upon lambda, HC, okay, and lambda in nanometer minus 5. Basically, what happens is actual value is 12375 upon lambda in angstrom. But if you write it in nanometer, 1237.5 upon lambda in angstrom. But for simplicity, I can write it as 1230 upon lambda. Okay, that is what I have done over here. Minus 5 should be equal to 1230 upon 400 minus 5. Okay, so how much will it be? 300 1230 upon 300 minus 25 equal to 1230 upon 400 minus 5. Alright, so 5 can be written as 152 is 5 is equals to 1230 divided upon 1/3 minus 1/4. So, so 1230 upon 100 into 4 minus 1 by 12. So 1230 upon 1200. So now you can calculate this. It will be something around 1.330300 1.02 electron volts, something like this. Okay, this will be your answer. Now, question number 21st. How many questions are there? Okay, so 8 questions. I will do it quickly. So, assuming an electron is confined to a 1 nanometer wide region, find the uncertainty momentum within Heisenberg uncertainty density. So, the principle is delta x multiplied with delta p is equals to h. Even this is the error in finding the location, the error in calculating the momentum is equals to h. You can assume the uncertainty position delta x as 1 nanometer. Assuming p equal to delta p, find the energy of the electron volts, all equivalent. So delta p is equal to h upon delta x is equal to h upon 2 pi delta x. Okay. So just have to put in the values over here. So delta p is equal to 6.6 into 10 raised to the power of minus 34 joules second, all divided by 2 into 22 by 7 into 10 raised to the power of minus 9 meters. Okay. Yeah, let me take off my calculator for this. So it is coming out to be 1.05 into 10 raised to the power of minus 25 kilogram meter per second. Okay. Now, if I want to write for the energy, it will be p square upon 2. So 1.05 into 10 raised to the power of minus 25, the whole square, all divided by 2 times 9.1 into 10 raised to the power of minus 31 kgs. Now, I'm solving this, you'll get the answer for energy as well. Okay, so now we have question number 22. We'll finish it off. So in question number 22, two monochromatic beams A and B of equal intensity I hit a screen. The number of photons hitting the screen by beam A is twice that by beam B. Two monochromatic beams are there, okay? Intensity is same, okay? Number of photons hitting the screen by beam A is 2 times that by beam 2. Okay, then what inference can you make about the frequencies? Okay, so I hope you know this graph for it. This is called a photoelectric effect. Okay, this is the potential that has to be stopped. Stopping potential is the current that is being flowing due to the movement of electrons. 1 and 2. If you raise the intensity, the stopping potential is the same. Only that the change is done in the current. Okay, but effect of this is for the effect of intensity. But if I draw for the effect of frequency, see, this is the intensity effect, and this is the frequency. So in the frequency effect, I will be constant, alright. But what is changing is the stopping potential. So current is same, but the stopping potential has shifted backwards. If you change the frequency, now To solve this question, let us assume Na is the number of photons falling per second of beam A. So beam A, say I am number of photons that are Na, and similarly beam B, say number of photons that are being emitted is NB. All right. And it is given that the number of photons hitting the screen is two times, so Na is two times NB. All right. So energy of falling photon on beam A, can you write that? Energy due to beam A will be equal to H nu A, and energy due to beam B will be H nu B. Okay. Now, according to the question, intensity of A is equal to the intensity of B. And what is intensity? Intensity is Na mu A equal to Nb mu B. Okay. So mu A upon mu B equal to Nb upon Na is equals to Nb upon 2 times Nb equals to 1 upon 2. So V mu A upon mu B is equals to 1 upon 2. So this is the equation. Now moving onwards to question number 23. So we have question number 23 over here. Two particles A and B of D probably wavelength A and combined to form a particle C. Okay, so particle A and B, particle A is there, particle B is there, they both combine and form a particle C. Yeah. The process conserves momentum when the de Broglie wavelength of the particle C. Okay. So since there is conservation of momentum, I can write momentum of C is equals to momentum of A plus momentum of B. Okay, it has a question itself. Now, okay. So relating through their lambdas, so 1 upon lambda C is equals to 1 upon lambda A plus 1 upon lambda B, because lambda is inversely proportional to momentum now. 1 upon lambda C will be equal to lambda A plus lambda B whole divided by lambda A lambda B. So I can write lambda C over here is lambda A times lambda B whole divided by lambda A plus lambda B. Okay, so this is lambda C. No, but we have to make some cases, right? See, now listen to me. We have taken PA and PB. It is not that both will always be positive. PA can be in I cap, PB can be minus I cap, so PB can be negative. So there will be cases. So we just find out for different cases, right? So this is the lambda C when both are positive. Both the momentums are positive, but when one of the momentum will be negative. 1 upon lambda C equals to 1 upon lambda A minus 1 upon lambda B, and similarly take for 1 upon lambda C is 1 upon lambda B minus 1 upon lambda A. These can be the other two cases, right? Either B will be positive, either C will be positive. If both are positive, then whatever was the first relation, you just put in a minus sign over there. Okay. So these are the four cases that will be there. So 1 upon lambda C will be equal to lambda B minus lambda A. Whole divided by lambda A into lambda B. Now writing down lambda C is equals to lambda A times lambda B divided by lambda B minus lambda A. Alright. And over here, similarly, 1 upon lambda C will be equal to lambda A minus lambda B. Lambda A multiplied with lambda B. And lambda C is equals to lambda A lambda B. Lambda A minus of lambda B. Alright. So these are case number 2, 3. 1 was over there, and 4 will be the minus of 1. Okay. So these are the 4 cases. Now, question number 24. So in question number 24, the neutron beam of energy is scattered from metal or a surface with spacing d equal to 0.1 nanometer. The first maximum intensity of the reflected beam occurs at theta equal to 30 degrees. Okay, what is the kinetic energy of the beam in electron volts? Question number. Okay. Question number 23. We have been question number 23. So question number 24. Yeah, I was reading it right. So question number 24 means a neutron beam of energy scatters from atoms on a surface with a spacing dV, the first maximum density of the reflected beam of itself. It is equal to 30 degrees. What is the kinetic energy E of the electron? E square by 2m. We have to get back to this question. We will hop on to question number 24 right now. Question number 25. Long answer kind of questions. So what do we have to do? We consider thin target. Okay. Thickness is 10 to the power minus millimeters. All right. Of sodium, which produces a photocurrent of 100 microampere when the light of intensity 100 watt per meter square. Okay, lambda has been given. Find the probability that photoelectron is produced when a photon strikes a sodium atom. Density of atom has also been given to us. Okay, so let's do this question. So the ionosphere area, which is 10 to the power of minus 2 centimeter square, and if I convert it in SI unit, it will be 10 to the power of minus 4 meter square. Already. Now thickness D, which I have is 10 to the power of minus 3 meter already given in SI unit. Photocurrent I has been given as 100 micros, so 100 into 10 to the power of minus 6 ampere, which is equal to 10 to the power of minus 4 ampere. Right? And intensity I has been given to me as 100 watt per meter square. Alright. Now, what if anything else? Lambda has been given as 660 nanometers. So 660 into 10 to the power of minus 9 meters. Alright. Now, density has been also given to us. See data, how much data has been given. So density will be rho equal to 0.97 kg per meter cube. Alright. So how can we do this question? We already know that 6 into 10 is to the power of minus 26 atoms of sodium will weigh how much? 23 kilograms, right? So since the density has been given to us, the volume of 6 into 10 is to the power of 26 sodium atoms will be 23 upon 0.97 cube. Okay, divided by density. Alright. So how much will it be? I'll just leave it like this for now. So the volume occupied by Na atom will be 23 divided by 0.97 into 6 into 10 to the power of 26. Into 10 to the power of 18. Okay. So now let n be the number of photons that are falling per second on the target. So energy will be hc by lambda already. hc by lambda is the energy. Total energy will be n times hc by lambda, where n is the number of electrons. So this can be written as intensity into area. So n can be written as I a lambda upon hc. Now we just have to put in the values over here. So put in the values over here. So when putting in the values, what will I have? I intensity 660 into 10 raised to the power of minus 9. 6.62 into 10 raised to the power of minus 54 into 3 into 10 raised to the power of 8. So this will come out to as so let me give the probability of emission per atom per photon. Okay, so I'll say the probability is P for the emission of electrons. Now I can write the number of electrons n as P times n into n of sodium. So P times 33 into 10 is to the power of 16, 3.3. Okay, into 2.53 into 10 is to the power of 18. So according to the question, we have been given that I is equals to what? 10 is to the power of minus 4 ampere. And I is equals to NE. So 10 is to the power of 4 is equals to probability P times the current 3.3 into 10 is to the power of 16 into 2.53 into 10 is to the power of 18 into 1.6 into 10 is to the power of minus 19. Okay, so on solving all of this, what will be it? 10 is to the power of 4 divided by all the other things. 10 is to the power of 4 divided by 3.3 into 10 is to the power of 16 divided by 2.53 into 10 is to the power of 18 divided by 1.6 into 10 is to the power of minus 19. Okay, so 7.48. 7.48 into 10 is to the power of minus 21. See the probability. This is the probability of photon emission by a single photon on a single atom. Okay. Now, moving on to question number 26. Question number 26. Consider an electron in front of a metallic surface. Okay. Distance d. Assume that forces of attraction by the plate has been given by 1 by 4 times q square upon 4 pi epsilon naught d square. Okay. Calculate work in taking the electron infinite distance from the plate. Okay. Simple. तो क्वेश्चन में दिया गया है फोर्स इलेक्ट्रोस्टैटिक फोर्स दैट is 1 by 4 times the normal q square upon 4 pi epsilon naught d square. Sorry. Okay. So let at any instant electron be at a distance x from the metal surface. Then we'll find the force of attraction. Then we'll just integrate it over f dx. Okay. So this is the metal disk. Okay. Distance d has been given 0.1 mm, right? And let's say the electron is at a distance of x from the metallic surface. Now the force that has been acting on it, F, electron and angle towards. The work done will be integration f dot dx that we already know. So we just write it over here. So work done will be from distance d to infinity q square upon 16 pi epsilon naught x square dx. Okay. So taking out the constants outside, q square upon 16 pi epsilon naught. Integration from d distance to infinity for dx upon x square. Okay. Simple integration. X raised to the power of minus 1. This I can write as q square upon 16 pi epsilon naught. 1 by x और उसकी minus 1 by x, I'm sorry. So एक minus sign आएगा 1 by x और उसकी लिमिट d डिस्टेंस दी हुई है 0.1 नैनोमीटर यानी 10 raised to the power of minus 10 मीटर से infinity. Okay. So simply put, work done की value हम निकाल लें. In 1 upon infinity 0 हो जाएगा, minus 1 upon 10 raised to the power of minus 10 minus plus हो जाएगा. तो अब पूरा आ गया है प्लस में. तो वर्क डन इज इक्वल्स टू पहले q स्क्वायर 1.6 into 10 raised to the power of minus 19 का होल स्क्वायर q स्क्वायर into 9 into 10 raised to the power of 9 whole divided by 4 into 10 raised to the power of minus 10 जूल. तो इसको रिवर्स सॉल्व कर लेंगे हम लोग. 1.6 into 10 raised to the power of minus 19 को अलग करके सॉल्व कर लेंगे तो इलेक्ट्रॉन वोल्ट्स में आंसर आ जाएगा. So it will be 9 into 1.6 that means 4.4.4936. So 3.6 electron volt is the answer for this question. Okay. Simple integration था, कुछ भी डरावना नहीं है इसमें. Now question number 27. So a student performs an experiment on photoelectric effects using two materials A and B. A plot of stopping potential V stop versus V versus mu frequency has been given in the figure. Which material A or B has a higher work function? First of all, answer this question for me. Work function, I told you that the minimum energy that is required. See, the threshold frequency is the minimum frequency of incident radiation that are required to eject the electron. Okay. So if the incident frequency will be less than the threshold frequency, there will be no photoelectric emission. First of all, you have to understand this. So जिसकी frequency ज़्यादा उसका वर्क फंक्शन ज़्यादा, सिंपली ऐसे कह सकते हैं उसको. जिसकी देखो एनर्जी क्या होती है, एनर्जी होती है एच न्यू, और यही होगा हमारा वर्क फंक्शन. जो जब हमारा एच न्यू सरपास करेगा हमारे वर्क फंक्शन को, तभी तो हमें काइनेटिक एनर्जी मिलेगी. एच न्यू माइनस फाइव, अगर काइनेटिक एनर्जी पॉजिटिव चाहिए तो एच न्यू मस्ट बी ग्रेटर देन फाइव. तो जिसका म्यू ज्यादा, जिसकी फ्रीक्वेंसी ज्यादा, मिनिमम इलेक्ट्रॉन निकालने की, पहले इलेक्ट्रॉन निकालने के लिए अगर किसी को लग रही है 100, किसी को लग रही है 200, तो जिसको 200 लग रही है उसका वर्क फंक्शन ज्यादा है ना. 200 हर्ट्ज किसी को लग रही है, किसी को 100 हर्ट्ज लग रही है, तो 200 वाले के लिए ज्यादा हो गया ना. तो सी यहाँ पे फ्रीक्वेंसी बी के लिए दी हुई है यहाँ पे, और उसके लिए कम दी हुई है 5 10 into 10 to the power 15 में जो भी लिखा 14, और इधर 5, तो 10 वाले की ज्यादा है, तो वर्क फंक्शन ऑफ बी ज्यादा हो गया. नाउ सेकेंड थिंग, अगली चीज क्या पूछ रहा है, अगली चीज है गिवन द इलेक्ट्रिक चार्ज ऑफ एन इलेक्ट्रॉन, find the value of h obtained from the experiment for both a and b. Okay, तो मेटल ए के लिए मैं स्लोप हो जाएगी हमारी h by e is equal to 2.5. हमारे लिए क्या होगा 15 minus 10 into 10 is to the power of 14. ठीक है, ये हो गया पहले की ढाई ई. तो यहाँ से आ जाएगा 2.5 into 10 into 1.6 into 10 is to the power of minus 90 divided by 5 into 10 is to the power of 14. तो वैल्यू ऑफ h आ जाएगी 0.88, 14 minus 5 minus 14, 33 को दे देंगे minus 34, so 8 into minus 34 joules second. So value of h from the experiment different आएगी दोनों से. ठीक है, एक्चुअल वैल्यू होती है 6.4. चलिए दूसरे की वैल्यू पहले की निकाल की करते हैं. पहले वाली क्या आ जाएगा h by e यानी 2e अपॉन 5 into 10 is to the power of 14. So इसको सॉल्व करेंगे 2 into 1.6 into 10 is to the power of minus 90 divided by 5 into 10 is to the power of 14. फिर से हो जाएगा minus 33 तक जाएगा ये. 3.2 यानी 6.4.64, तो 6.4 into 10 is to the power of minus 34 joules. जूल सेकंड, आई एम सॉरी. तो ये एक्सपेरिमेंटल वैल्यू 1, ये 2, तो डिफरेंट आ रही है 2 के लिए. ओके, सो नाउ वी हैव क्वेश्चन नंबर 28. लास्ट इज क्वेश्चन नंबर 29. So a particle A with a mass m is moving with a velocity v and it hits a particle B of mass mb, which is at rest initially. Now we have to find the change in the de Broglie wavelength of the particle A. We have to treat the collision as elastic. So in elastic collision, so first of all I can say the momentum has been conserved. Okay, so ma, I'll consider the velocity b minus v1 is equal to m times b v2. Alright. Now another thing I can do, half mAv square, since there is no collision, half mb, velocity of b is 0. This must be equal to half mAv v1 plus square plus half mb v2 whole square. Now mAv square minus v1 plus square equal to mb v2 plus square. So m is v minus v1, v plus v1 equal to mv v2 plus square. So dividing equation 2 by equation 1, you can simply get v2 equal to v1 plus v and v is equals to v2 minus v1. Now solving further, now momentum MAV minus MAV1 equal to MB V plus V1. If you put the 3 in 1, alright, putting the value for it. Now MAV minus MAV1 equal to MBV plus MBV1. Now MA minus MB V is equals to V1 MA plus MB. Simple. So V1 will be MA minus MB, MA plus MB times V. So solving further, I'll get V2 is equals to V plus MA minus MB all divided by MA plus MB into V. So we'll take out V common from it. And from question number 2 that I found earlier, I can write MA plus MB. I'm taking V common out, right? So MA minus MB. I've taken out V common all divided by MA plus MB. So this will be equal to 2 times MAV all divided by MA plus MB. So lambda A in initial was H upon MAV, and lambda A final will be H upon MAV. Now if I want to write the change for delta lambda, it will be, I'll take MAV common as it is, MA plus MB, MA minus MB minus 1. So this will be your delta lambda for this question. Okay. Now moving on to the last question. Yeah. So according to the question, this 5,000 from research what is water function as a select is already taken. There's one number of photons per week per second. Okay. So first of all, power has been given to the 20 watt. Lambda has been provided 5,000 angstrom. Alright. Distance D has been given to me as 2 meter. Work function is 2 electron volt, and radius I can take as 1.5 angstrom. That is 2 power of minus 10 meter. So first of all, part 1, number of photons emitted per second by the bulb is N dash is equal to P upon Hc by lambda. So P lambda upon Hc. So 20 into 5,000 into 10 to the power of minus 10 upon H 6.6 into 10 to the power of minus 34 into C3 into 10 to the power of 8. So this will be an answer for number of photons that have been emitted in case 1. Number 2. Case number 2. So case number 2 is, will there be a photoelectric emission? We can check. We have to check for Hc by lambda equal to 6.6 into 10 to the power of minus 34 into 3 into 10 to the power of 8 all divided by 5,000 angstrom into 1.6 into 10 to the power of minus 19. So whatever energy comes out of this, the work function has been given as 2 electron volts. So if it will be the energy which is coming out of this, if this energy is greater than work function, that is 2 electron volt, then photoelectric emission will happen. Otherwise, no. So moving on to the next part. So there is question number 3 for us. So how much time would be required by the atomic disk to receive energy equal to work function 2 electron volts? Okay. So P upon 4 pi d square into pi r square delta t equal to work function final that has been given to us. So delta t I can write as 4 into 6 into 10 to the power minus 19 for d square into square all divided by 20 into 1.5 into 10 to the power of minus 10 whole square to solve for this. Now number 4. So how many photons would atomic disk receive within time duration calculated in C above? So we have to find n. N will be equal to n dash pi r square upon 4 pi d square into delta t. Okay, this is the delta t. You will put it over here, and these are the values that you already. So the answer will be whatever the solution for this. The last part is, can you explain how photoelectric effect was observed instantaneously? All right. In photoelectric emission, there is a collision. Okay, I already told you there is collision of electrons between the incident photon and the free electron also. So this will last for a very short interval of time. In the in the matter for nanoseconds. So then we can say that the photoelectric emission is instantaneous if the emission can be detected within in the range of nanoseconds. So that will be the answer for this as well. So I hope to see you in the next class, and thank you for your time. Bye bye.